Hello and welcome to our talk today. I'm going to present a piece of research that was done in the context of the AI Multiply project, which is funded by NIHR in the UK. And you can see from the list of authors, this is a collective piece of work. The first author, Hugo, is a former postgrad student of ours who did much of the work. This is a work taken from his final project, his dissertation. And my name is Paolo Missier, and Multiply is a consortium consisting of co-Is from Newcastle University and Queen Mary's University, London. This is a paper that was presented at the Big Data Analytics for Health and Medicine workshop at the Big Data conference in mid-December 2023. So this is a recording of the talk. We're going to talk about interpretable hospital readmission predictions using electronic health records. And I'm going to introduce the topic as a combination of, okay, what is multimorbidity, what is polypharmacy, hospital readmission. These are the key concepts behind this work. So hospital readmission is, we define it as, per the literature, as an unplanned readmission to hospital within 30 days of discharge, regardless of the initial diagnosis and regardless of the reason for the admission. It's just unplanned. Typically, this is a well-studied problem, but it's studied in the context of a single condition using limited medical history. So instead, our focus is on multiple long-term conditions. So long-term conditions, chronic conditions, according to the NHS as a reference down there, and multiple long-term conditions are usually defined as 2 or more LTCs or 4 or more. So we use 2 or more in this context. Polypharmacy is the occurrence of multiple prescriptions that overlap in time, and how many you have accumulated at a given point of time is kind of a variable threshold. We actually use all prescription history that is both historical and prescriptions at the time of the original admission. So why is this an important problem? There's obviously economic burden on hospitals, and the data down there will give you a perception of how big it is, but obviously there's also a quality of life issue for individuals, and so we try to address both in this study. So what this study aims to do is to develop a machine learning model for hospital readmission, where the focus is on specifically on multiple long-term condition patients. The data set is biobank, and biobank, as I'll say in a minute, has linkages to primary and secondary care records, and that's basically longitudinal depth that we're going to use in our study. We also include socioeconomic features which come to us from the biobank. This is a good characterization of participants in the biobank. And we use the linkages to secondary care records to access drug prescriptions at pre-admission stage, and those in the primary care records to access prescriptions through the entire life course. And we aim for our model to be robust, to class imbalance and explainable, and these are two typical requirements of workable machine learning models, where the class imbalance comes from the fact that many more people have not readmitted than have been readmitted. So if you want to use the entire training set, then you somehow have to amplify the minority class or somehow account for this imbalance. So we're not the first, as I said, to do this. There are prior results. This table is not super recent, but the key point here is that some of the work that we came across is really performed in the context of specific key conditions or index conditions, as they say, and the results are not particularly exciting. So in this talk, I'll talk about the nature of the trend and the shape of the trend data set and how we characterize the outcome, which is readmission. We talk about class imbalance and feature selection, because we'll see that the, the shape of the data set is such that there is a proliferation of features. And after giving some of the results, I'll talk about explainability and feature importance. There are some limitations that we'll touch upon towards the end. Okay, training data set. The UK Biobank is a very popular data set to use. Is not entirely freely available, but you can access it worldwide through an application to Biobank for research purposes. It consists of 500,000 participants who are all baselined, age 40 to 69. And what is really interesting in our context is that they link out to primary data, as I said, for about 40% of these participants. And I should also say they link out to, well, we can reach out to, we can link to HESIN data, which gives us secondary care records, which means hospital admissions and hospital episodes. There's lots of information in the electronic health records of EHR. We do not look at clinical tests, and in fact, we only use as inclusion criteria a predefined list of 203 long-term conditions that we have pre-selected as part of the work done in the consortium, and then included only those that have 2 or more of those. And that gives us about 70,000 records to work with. And each record is a patient timeline that can span up to 20 years of time. What is the complete characterization of patients here? Many features aside, there's about 1,300 features, of which the vast majority is categorical. And the reason there are so many features is that we divide them in five categories, and some of these are actually obtained through one-hot encoding of categorical, of processing the timeline. So specifically, we use admission data, which is basically the duration of the first admission, the primary diagnosis at admission. We then use demographic features and lifestyle features that come to us from the biobank. And this is a list. And these have been selected as the most promising features which would correlate with multiple long-term conditions, as well as possible propensity to hospital admission. There are many others that we haven't really considered, and those can be added. We have access to hundreds of features, but by and large, demographic and lifestyle features are these. And then there's a list of diagnoses. So this is imagine a matrix, a patient by condition matrix, and with it's a binary matrix with a 1 in a cell where patient X has condition Y and 0 otherwise. So you can one-hot encode these, and obtaining basically one row of the matrix characterizes the long-term condition profile of one patient, although it should be noted that we do not use the time in this case. So basically, we just use the bit vector. And we do the same for drug prescriptions throughout the timeline. Again, it's a 1 if patient X has ever been prescribed drug Y, but the drugs are actually encoded using the BNF, which is a UK specific taxonomy of drug prescriptions. And we stop at a particular level in the taxonomy called the subparagraph level. We also have access to the drug prescription that are active when the patient is readmitted. Okay, what about the outcome? The outcome is a single state yes or no according to the criteria. We get that from the HESIN, which is the hospital statistic data, when there is a link to patients. And importantly, when the record doesn't say, well, there are no records about readmission, we just say the patient has not been readmitted, which is an assumption of completeness of HESIN data. So A non-existent record for readmission does not mean that we don't know. It means that we know it has not been readmitted. And this is an important assumption that we make. As I said, there is a class imbalance. This is about for each non-readmitted, for each readmitted patient, there's about 3 have not been readmitted in this cohort. Okay, so the first thing we try to do is reduce the number of the 13,000 features, and the first approach is do any of these check whether any of these features correlate with the outcome. Highly correlated variable state priority, this is like textbook data preprocessing. However, we find that this is not very promising in this case because the univariate correlations exhibit very low values. So the chart here, the plot shows that there are a few variables that are higher correlated than others, but on average, they are all the correlation values, absolute values are really small. So it's only 22 features are greater than 1, but only 2 greater than 0.3. This indicates that we can't really use this technique to select reliably or filter out some of the features. Instead, what we've done is use hypothesis testing, which really means look at the distribution of the variables, which are the continuous variables or discrete variables, test whether the distributions are significantly different in the negative and positive classes. And there's a detail here of how this is done for continuous versus discrete variables. Details are not particularly interesting because they are not used. It's just kind of standard testing, statistical testing. The outcomes indicate that at 0.05 confidence level, we come up with about 740 features that are relevant for admission, some of which are, significantly, very significantly, different between the two outcomes. And there's a description here of how they break down. Basically, we pick up 80% of demographic features. We only pick up 25% of the LTCs, which really means 25% of the conditions. I don't have a list of conditions here, but these are the numbers in aggregate. And the second thing is class imbalance. And again, there are various ways to deal with it. The first attempt here is to amplify the minority class. Now, because the vast majority of these features are categorical, we cannot use techniques like SMOTI, which have been, or maybe there are categorical variations for SMOTI, but this is not well used. Instead, kind of more ambitiously, we went into generative adversarial network territory. And there are a variety of GAN architectures that have been suggested to generate synthetic tabular data, which is our case. And the advantage of those is that they're suitable for both mixed type and numerical, mixed type data, so both numerical and categorical variables. The authors of the reference paper that we use down here, number 1, which is the NeurIPS 2019 paper, make claims that this is state of the art, considering other, that has actually been shown to be superior to TVA. Now, more in detail, if you accept that CT-GAN can generate synthetic data, then the next question is how well does it represent, how well does it actually amplify the minority class? There are a variety of metrics to measure the quality of synthetic data. In this case, we use for continuous variables and categorical variables two metrics, which are Kolmogorov's statistics that defined. The definition here is not exactly correct in terms of or accurate in terms of equation, but this is it's basically the attempt here is to compare fs and fr of x for a sample X and determine whether they come from the same cumulative distribution. More details are actually in the paper. For categorical variables, we use something called the total variation distance, where RW and SW represent the frequency of a particular category W, which appears in the column omega. So for each column omega, which is categorical, we take the categories, and then we just count the frequency of occurrences for each of the categories in omega. Importantly, we also use a pairwise correlation distance, PCD, defined as here. And that is important because the results that we see is that we get very high distribution similarity using the KS and TVD for continuous and discrete respectively across variables. And we've been able to fine-tune the models in terms of hyperparameters to achieve a very high distribution similarity. However, it has been more disappointing to see the PCD values, is basically the pairwise correlation values, are in a high range, and PCD is, the smaller the better, and ideally we would like to see numbers close to zero here. So this is to say that CT-GAN in this case does not really reproduce, well, it reproduces individual, univariate distributions that make sense, but it does not reproduce in a way that it preserves the correlations amongst the variables. So in the end, we discarded this approach, and instead we resorted to well-known cost-centered learning techniques, which is basically a well-known way to modify the loss function used by the gradient descent in this case, by typically adding a cost matrix where the cost of ij represent the cost of misclassifying instance of class I as class J. So basically, it introduces explicit bias that kind of compensates for the natural imbalance in the classes. These improve generalization, but okay, this is again kind of textbook machine learning, so we just apply this technique. Finally, how we did the classification. This is a standard binary classifier, so XGBoost tends to dominate the landscape in this case. And we tried a few, and we only published the results for XGBoost. It's robust to overfitting, and it accepts the modified loss function for cost-sensitive learning. So it all works very, very nicely. In terms of comparing comparing the results, we compare the full feature set with the selected feature version of the training set, and this is because you want to verify that if you throw away some of the features, then the loss of performance is acceptable, which in this case gives you an opportunity or a trade-off between a linear model, which is generally preferred, with fewer features at the cost of a small performance decrease, versus a full fat model for full performance. Okay, so we explore this trade-off. Again, I'm just reporting here on the hyperparameters here. The results are fairly simple here to report. All features versus select features. Scroll down to AUC, where the results are very, very similar, and they're also very similar in all other metrics. And what is really interesting is that sensitivity and specificity are quite close, in the sense that we can claim that we're able to predict both classes almost equally well. F1 is very high, AUC is very high, accuracy is very high, everything looks promising. And the AUC from here, you see that selected features do sacrifice a little bit of performance. So on balance, then the main author, Ugo, decided to go with the full fat model to add explainability features. And by comparison with prior work, this is the table that I reported at the beginning. And as we can see, we are way above those numbers in terms of performance. When it comes to interpretability, sharp plots are your friends. They work very well XGBoost. Again, there's nothing much to invent here, but it is a good confirmation that of the relative importance of each of the variables, of the features, which is basically feeds discussion with the clinical team in our multiply consortium. So age of event and LTC count, the duration of first admission, the fact that you had historical prescriptions or no, and then a number of other more specific features. They contribute in various ways. Okay. And the plot comes with the relative importance at the population level. So we haven't done individual level analysis here. What we have done, however, is added a second measure of relevance, and this is known as accumulated local effects, which basically works by estimating the effect of a particular feature xi by marginalizing essentially all other features and averaging the effect of those other features. So if we pick the three, I'm going back here, the three top features from the sharp value, we now have a more granular view of how the values of these features affect a prediction. So now this becomes a function of the feature value. And we can see the age of event here. There's a strong knee here. Remember, okay, basically the 30 is not sure about the 30 because we really start at 40 here. But between 50 and 60, there's a strong increase in the importance. So in the importance of age of event. So this means that the age event features becomes more prevalent for as you progress with age. Similarly, the first admission duration here is basically there's a peak here and then it's fairly stable. Also importantly, the number of LTC counts then goes up rapidly up to about 8 and then increases more slowly, which means that as you increase the number of LTC counts, the importance of that number increases in terms of this side determining your outcome. Okay. But it is monotonically increasing, at least for the first two variables. Finally, we did an ablation study at the level of feature set, not individual features. Now we aggregate these 5 feature sets, basically admission feature, demographics, historical, and pre-admission prescriptions, and then LTCs, to see whether by removing selectively one of these feature sets, we would compromise performance, indicating that that feature set is actually important. The results indicate that, yes, there are differences, but the numbers are so small that we can conclude that each of the feature sets are participating in the prediction, not equally, but in a way that, yeah, it's fairly within a really small range. So the indication is not to discard any of these feature sets. Okay, in conclusion, what we've done is we've done a machine learning exercise to predict hospital readmission for MLTC patients through a robust process of learning a classifier. We use 5 feature sets, which is more than we have found in the literature. We achieve state-of-the-art performance. And we have shown that demographic variables in historical prescription show higher importance, but age, number of long-term cognition, duration of first admission are also important as individual features. There are limitations in that the study was only done on the UK Biobank with no independent validation data set, so that is coming in future work. We only use XGBoost. We're quite confident that this is hard to beat, but for completeness, we will then search through a space of machine learning models. We could have included other features, for example, from wearables, intensity of physical activity, and other such features. Again, expanding on the feature set is left for future work. And with that, I'd like to thank you for your attention and for listening this far. Thank you. And actually, to conclude, I would like to show the acknowledgement slide where this is actually not the entire, I think, consortium, but I would like to thank all the collaborators for participating in this work. Thank you very much.